we will have Thomas here giving us a speech about music tuning, which is quite interesting with Julia. It's quite different from everything we had in this morning so far. So yes, let's get ready and welcome Thomas for the speech.
Thank you. More specifically about music tuning. So tuning is putting frequencies onto notes, and this is a package that I wrote for this. It's not registered yet, so you can still influence the name if you don't like it. I call it tuning systems for now. So we all know if you look at the normal piano, we have the octave divided into 12 equally distributed frequencies, the 12 semitones, and they each have a frequency ratio of about 1.06. So the package has a function to generate these equal tempered scales of any length. So here it is of length 12, the normal one. And it also has a method to generate a data frame out of this so that we can do computations on this. It can also play, and this is going to be the interesting part. So it can actually play a scale, and what I do here is, so I have the note names here, then I just do a split, then the note function generates a note, the tone then takes that note plus a tuning, and in this case it's the equal tempered 12 tones, and then it generates a sound with a synthesizer, and then it plays this out of that. So it seemed to work this time, that was nice. So some sounds sound particularly nice. So for instance, the octave, or the fifth, and they are, here we play them together. And you can see in the way this is done, so here in the first one, I just, if I take the sound on the vector, it plays the chord, and if I broadcast it over the vector, then it plays them in sequence. So that, I think that's a pretty nice interface for this. Right, so how well is the piano actually tuned? So if we look at the difference between the perfect fifth and then the seventh semitone on the piano, we can see on this number up here that they are pretty close. They are within 0.1%. Or something similar. So how does this actually sound? So we can hear if we play them together, we can hear that there's actually a small beat tone like this. If we play them without play them in succession, you need to have very good ears to hear that were actually two different tones. So this is some of the fun things that you can do. There's also plot recipes that will then plot the two together so that we can see how they look as functions. And this was the beat tone, so you can also, if you plot this over the beat frequency, which is 0.75, which is the difference between the frequencies, then you see this. And in order to do this in a good one, you actually explicitly have to sample. And the sample method is doing that at a normal 41K, and also for the plotting. Okay, so the equal tempered tuning is so natural, it spreads evenly, why would you ever have anything else? But it turns out that other cultures, other times have used other tunings. So one of them is, it's this guy, Pythagorean. Apparently, I don't know it, I'm told, he was thinking about these things, and he noticed that if you take this fifth, which sounds perfectly, and if you apply it 12 times, so you know mathematicians, if it works once nicely, then just do it twice, just keep doing it. If you do it 12 times, you actually get to something which is almost 7 octaves higher. And the difference is this little bit, this funny looking fraction, which is called the Pythagorean comma. And this comma is actually not so small. So if which slide am I on? Right, so, sorry. Okay, I'll skip that. So I can also play the comma, and it has a beat frequency of about 7 hertz, so it can it's actually hearable. Yes. I want to introduce two other concepts that the package understands. So there's pitch classes, which are basically equivalence classes of tones given a module or an octave. And there's cents. So cents are the 1200 division of the octave. So if we do this thing about going off the fifths and do the pitch class and then take the cents, we can see that we get something which is almost a integer times 100, but it's overshooting by about 2 every time. So when we've done it 12 times, we're overshooting by almost 24. So in reality, the Pythagorean tuning is sort of halving this error by going both ways around the circle of fifths and putting it all the way over to the tritone, which is F sharp, no pun intended. That is what is actually called the Pythagorean tuning, and the package has that inbuilt. So I just want to do a little bit of plug for this tuning, which is called just intonation, and where all of the 12 semitones are in nice little fractions, which are composed by numbers that are multiples of 2, 3, and 5, so it's called a 5-element tuning. There's another plot recipe in the package to plot tunings, to compare them on a cent scale. So here we can see how they look if we compare them together. And then the last thing I want to talk about is the harmonic series. So if you take the first 6 harmonics, or the first 5 actually, you get three different frequency ratios, and that is actually the major triad. Yeah, I would also like to play that, but my history just went wrong. So I hope I get to it in the end if I have time. Anyway, here's how it looks on this. So if we take a lot of harmonics, we can almost get this tuning, but not quite. I wanted to get to this slide because one nice thing about the just intonation is if you take the sort of 3 major chords, if you play a guitar, you know 3 chords, it's these 3 chords. If you take those, then for all of these 3 chords, you actually have the same ratio between the frequencies, so 4, 5, 6. And if I'm a little bit lucky, I can make this play so that I can and this was actually what I wanted to sort of investigate with this package, was how does this actually sound? I mean, if I take this major triad and play it in these different tunings, then how does this actually sound? And while you're thinking about your questions, then I'll see if I can find this in my REPL history so you can hear it. So here comes the... So this is the just tuning, and if we hear it now in, let's see, here's the equal temper. You see it's not so nice, it has a little bit of beating, and if we take the Pythagorean, it's actually pretty bad. So let's go back to the just one and then end that. Perfect harmony. Thank you very much.
Oh, this very interesting speech. Any questions about what happened earlier?
Yeah, I forgot. Thank you for all of the great packages of the Julia Music organization. And this was inspired by these very interesting blog posts by John Baez. So check them out if you're interested in things like that.
I just wanted to ask how much you enjoyed the keynote yesterday.
Very much.
And then I just wanted to suggest that you put music or something somewhere in the package name, because if I hear tuning, I think of like machine learning stuff. Yeah. And then I was like, this is really
music
cool.
tuning systems is probably a better name. So it's good that I didn't register it.
It's very, very cool. Thanks.
Which kind of waveforms you use for the examples?
All of this is just sine waves.
Yeah, because the beating is more evident when you use, because usually these are a bit more washed up when you have.
Sure, but this was harmonic for analytical purposes, so that's why I used the sine phone to make this clear. Of course, if you play it on a real instrument, it doesn't sound that bad. Otherwise, you wouldn't make music today, I guess.
Okay.